In weeks 1 and 2, we looked at a school database that was used by the English teacher, the math teacher, and the soccer coach. And I mentioned after we went through a revision of the database that we weren't quite done yet. So just as a reminder, these were the 3 spreadsheets that the English teacher, math teacher, and soccer coach originally kept. And this is the first version of the database that we talked about in week 2. When we set up our tables in the database, we want to make sure that all of the attributes, all of the columns in any one table are related back to the primary key. The primary key is normally put in the first column. It doesn't have to be, but that's the convention. And a primary key uniquely identifies each row in the table. So in the student table, the primary key is student ID, and all of the other columns in the student table are related to the student. In the parent table, the unique identifier is parent ID, and all of the columns in the parent table are related to a particular parent. Now, in order to relate 2 tables together, we need to have a foreign key in one of those tables that matches the primary key in the other table. So if we have 2 tables, we have 2 choices for where we might put the primary key. So let's see where that would work. A student could have more than one parent, so we can't just stick parent ID as a column for the foreign key in student, because we might have to cram 2 parent IDs into one line item for a student, and that's not allowed. We're only allowed to have one piece of data in each attribute for each row. So let's try the reverse. Let's see if we can put student ID in the parent table. Since a parent might have more than one student, we got the same problem again. So when we have this situation where one table can occur multiple times in relationship to another table, and when we look at the reverse, we still have the second table occurring multiple times in relationship to the first, we got a problem with where we put the foreign key. So the way we solve this is to create a third table called an association table, and in this case the primary key is the composite of student ID and parent ID. The combination of those 2 attributes uniquely identifies each row. Student ID is the foreign key in the student parent table to match back to student ID in the student table, and parent ID is the foreign key to match back to parent ID in the parent table. So if we have 3 tables that we're going to match together, we're going to need 2 foreign keys. In this case, student ID is one and parent ID is the other. You might recall in week 4 that when we were using tables that had nulls, sometimes that caused problems with our queries. And we have a bunch of nulls in the parent table because not every parent has supplied more than one phone number. And we also have some nulls in the student table. So let's take a look at some additional things we can do to improve upon this particular layout. One improvement is to take the phone numbers out of the parent table and to put them in their own table. So in this case, we have a composite key in the phone table of parent ID and phone ID. Parent ID is the foreign key in the phone table to match back to parent ID in the parent table. This is a better design because we've eliminated the nulls, and we also have more flexibility. If a parent has more than 2 phone numbers, we can easily store that as an additional row in this table. Now we could have done this a little bit differently. Instead of having 3 columns in our phone table, we could have had 2 columns. Parent ID and phone number could be the composite key. I chose to add a 3rd column so that I could distinguish between the primary phone number and the secondary phone number. But either solution would work. An additional change that I made was to set up a grade table. In our current requirement, we only need to know the English and math scores, but in the future we might need to know the history and science scores, for instance. And if we set up a separate grade table, this will give us the flexibility for adding additional rows for different types of courses. In the grade table, we have a composite key, student ID, and course uniquely identifies each row. If we have an additional attribute, that attribute has to be related to the whole primary key, both student ID and course. So in this case, the grade is indeed related to a particular course for a particular student. In the grade table, student ID is the foreign key to match back to student. So this is an improvement, but with this particular setup, we can easily store the information that is needed by the soccer team, but we might need to have the flexibility of showing additional teams. So in order to set this up for additional teams, we might want to have an additional table. In this case, I've called it the sports table, where we have a composite ID of the team and the student ID. Now, a lot of times we don't want to have a long name as part of our primary key, like soccer and baseball. The reason we don't want to have a long name as part of our key is if it's long, it can cause, it's more likely that we might have a typo, and we don't want to have any typos in our primary key. So a lot of times we would go with an abbreviation, as I did in the grade table, abbreviating the course to a 3-letter acronym. But I decided to, in this case, leave the team as the text instead of abbreviating that to a shorter team ID. In the sports table, the student ID is the foreign key to match back to student. As I mentioned on the previous slide, any attributes should relate to the entire primary key. So shirt size, we need to think about, is that related to the student or is that related to the type of shirt for a particular team and the student who's going to wear it? So because shirt sizes aren't standardized, and in this particular case, student 25901 wears a small shirt size for soccer but needs a medium size for baseball. In this case, shirt size is related to the combination of team and student ID. So this attribute belongs in the sports table rather than as an attribute that relates just to the student. The attribute of shirt size relates to the combination of student and team. So when you create your own databases, there are some things that you ought to be doing. Every column of data should have the data in the same format. Within a particular column, you should not have multiple pieces of data. So for instance, it's better to separate first name, initial, and last name than to just have a column called name. Likewise, in each column, for each row, there should be only one entry. It's against the rules to cram multiple pieces of data into a single column for a single row. Every table must have a primary key. The primary key uniquely identifies each row. In some cases, we might need two columns to uniquely identify each row. Second, all of the columns in the table should relate back to the primary key. And if we have a composite primary key, as we do in the sports table, the non-key attributes should relate back to the entire primary key, related to the combination of student and team. So these are called the rules of normalization. The first rule of normalization is we have a primary key that uniquely identifies each row, and we don't have any repeating data in any particular column. The second rule is that all of the columns relate back to the primary key. The third rule is all of the non-key columns in a table relate back to the primary key, the whole key, and nothing but the key. So that applies when we have tables that have a composite primary key, where two or more attributes are needed to uniquely identify each row. The way to remember that third rule is it's very similar to the truth, the whole truth, and nothing but the truth. Every non-key attribute has to relate back to the key, the whole key, and nothing but the key. The reason that we have these rules is we want to set up our data tables so that a piece of data appears only once in the database. So for instance, if we need to update the shirt size for a particular soccer student, we can update that in one place. Or if we need to update a phone number, we can update it in one place. This avoids a problem that's common if databases aren't designed correctly, where one piece of data conflicts with an updated piece of data somewhere else, and we don't know which version is the correct version. So we can avoid that altogether if every non-key attribute is stored only once in our database, and therefore it gets updated in only one place. Now, many of you in week 2 noted that our databases can get more complicated from a query point of view when we have these additional tables, and the reason we create these additional tables is so that we only store the data once and avoid a lot of null data in the database. And the whole purpose of designing transactional systems is to make it easy to update the data. We're not necessarily trying to make it as easy as possible to extract the data. So you're absolutely right. Sometimes extracting the data gets complicated when we have more tables, but it saves a lot of headaches if each piece of data is stored only once in the database, so that when it's changed, it only has to be changed in one place. So I hope this video helps you as you lay out your tables for your Week 7 project. It's very helpful to create some sample data to make sure that you've thought through the various items I've included in this videotape, and I'm interested in seeing all of your projects. If you have any questions, please drop me an email. Thanks.